us to get a good future. Thank you.
Yeah, welcome learners. Uh, Today I am here to discuss with you a very simple and elegant algorithm, uh, which is known as greedy coloring algorithm. So this algorithm is used to color the vertices of a graph. So we shall look at this algorithm, how it works through examples, and then we shall look at some results related to the chromatic number of a graph, which we shall see how to find the upper bounds and some lower bounds using this simple algorithm. So, in the while discussing this algorithm, we need to know what we mean by vertex coloring or coloring the vertices of graph. So, the idea is very simple. You are given a graph and you have to color the vertices of the graph in such a way that whenever two vertices are adjacent, they get distinct colors. So we shall also define what it formally means. So when we use use of vertex coloring, we get some interesting results, and that is what we shall discuss in this session. So let's first begin with the concept of vertex coloring. So the vertex coloring of a graph is defined as follows. A k vertex coloring on a graph G is a function f from its vertex set Vg to the set of elements 1, 2, 3 up to k in such a way that Fu and Fv are distinct whenever u and v are adjacent. So now it means that whenever u and v are two vertices which are neighbors, which are adjacent to each other, they must always get distinct colors. So the numbers 1, 2, 3 up to k, these are called colors. So the term coloring actually comes from the real scenario where you will, when the graphs are actually small, then they can be colored with real colors, red, green, blue, like this. So so when the graph is large, of course we cannot use real colors. We just replace the colors with some numbers, natural numbers. In that way, function f that that is defined on the vertex set to the set of elements from 1 to k is called a vertex coloring, k vertex coloring, if it uses k colors in such a way that whenever two vertices are adjacent, they get distinct colors. So that is the primary requirement for k vertex coloring. Okay, so when vertex coloring is given, our emphasis is on defining or finding the vertex k vertex coloring where k is as small as possible. So next comes the definition of chromatic number or vertex chromatic number. So a k vertex coloring on a graph G with minimum k is called an optimal vertex coloring of G, and then in such a case G is said to be k vertex chromatic or just k chromatic. So to find the chromatic number, we need to find a k vertex coloring of a graph where k is as small as possible. So in notation we shall write chi g equal to k, so that G is k chromatic, or G has vertex chromatic number k. And when chi g is less than or equal to k, in that case we say that G is k vertex colorable. So with these definitions, let's look at some example. So you are given a graph here. It has been actually colored using 3 distinct colors: red, green and blue. So the first thing that you can see is that the colors which have been assigned here just produce a proper coloring, a valid coloring. That is, look at any two vertices of the same color. You will see that there is no edge between those vertices. Like for instance, look at the green vertices, you will see that these form an independent set. Likewise, the vertices which are red, they also form an independent set. And since the blue one is only single vertex, so it forms a independent set. So in that way, we can see that the coloring is valid and it uses 3 colors, and therefore its chromatic number is at most 3. Okay. Now let's see whether there is a possibility of coloring this graph with fewer colors. That means, can you color it with just 2 colors? The answer is no. Why? Because there is some hidden structure in this graph. Just look at this triangle, the red, green and blue. The 3 vertices, you can see that they are adjacent to each other, and therefore in any vertex coloring they must get distinct colors. So 3 is what is the minimum number of colors that are required to color this graph, and just we have seen that 3 is also the maximum. Therefore this graph requires exactly 3 colors, and hence it is 3 chromatic or 3 vertex chromatic. Okay, now let's look at some simple small graphs where we can compute the chromatic number easily. For instance, suppose you wish to compute the chromatic number of a path on n vertices. So for let's look at a specific case, just path on 5 vertices. So that graph is given here. V1, V2, V3, V4, V5. There are 5 vertices. So you can just color the vertices alternatively with 2 colors, say red and blue. So the vertices which are indexed with odd numbers, say V1, V3 and V5, which so these vertices have been assigned 1 color, that is red one, and the vertices which are even numbered, that is V2 and V4, they have been assigned different color, the blue one. So in this case we see that P5 can be colored with just 2 colors, and it of course 2 is the minimum, because you cannot color it with just 1 color. It is just a simple fact. If a graph has at least 1 edge, then it requires at least 2 colors. Right. So now it can be extended to find the chromatic number of the path on n vertices. So you just extend this vertex coloring to any number of vertices. You will see that there are only just 2 colors that we need. Okay. In fact, this coloring can also be extended to cycles of even length. How? So you can just divide the cycle into 2 groups, the vertices of the cycle into 2 groups. The vertices which have been numbered say with the odd index, and the vertices with the even index. So the odd index vertices all are non-adjacent pairwise, and therefore they can be assigned the same color, let's say color number 1, and then the vertices which are even numbered, they can also be assigned the same color, say color number 2. So in this way, any even cycle can be colored with just 2 colors. So chromatic number of Cn is 2 for all n even numbers. Okay, so now of course n must be greater than or equal to 4. So now we come to the case of odd cycles. What happens to the chromatic number when we are given an odd cycle? So for instance, we have just seen the case of a triangle. So when we have a triangle, we see that the vertices are adjacent to each other. They are mutually adjacent. So in that case, such a coloring must require at least 3 colors. So chromatic number of a cycle, I mean a triangle, is just 3. Okay, what about a cycle of length 5, C5? So let's see how we can color this. So suppose you start with the color with this vertex. We start with the color blue and keep on coloring with alternately, and then say red, and then blue, and then red. So now we come at this vertex. So here again we see that the vertices which have been colored, say red and blue, they are both adjacent to the green one. So this vertex cannot be colored by the color red one and neither by the blue one. So we need a third color, say green. So therefore C5 requires 3 colors, and in fact now you can extend this argument to any general odd cycle. So you can just see that any odd cycle requires at least 3 colors, and in fact 3 colors are sufficient. Therefore any odd cycle can be any odd cycle has just 3 colors to color it. So we have just seen that chi-cn is 3 for all odd n greater than equal to 3. Now what happens when you are given a graph which has an odd cycle as a subgraph? How would you color it, or how many colors would you need at the least? So for a graph that has an odd cycle, we have seen that the odd cycle requires at least 3 colors. So no matter what other vertices are, how other vertices are colored, so 3 colors must be needed at the least. You cannot do with 2 colors. So for any such graph which has an odd cycle, its chromatic number is at least 3. Likewise, now suppose you wish to compute the chromatic number of a bipartite graph. So for a bipartite graph, you know that its vertex set can be partitioned into 2 disjoint sets, and in such a way that the sets are independent. So one of the set can be assigned one color and the other set can be assigned second color. So for any bipartite graph, of course the bipartite graph must have at least one edge. So for any bipartite graph having at least one edge, it can be colored with 2 colors, with exactly 2 colors. So the chromatic number of a bipartite graph or non-null bipartite graph is just 2. So in particular, suppose you wish to compute the chromatic number of a complete bipartite graph Kmn, then its chromatic number is also 2. Just a special case is given here. The chromatic number of K24 is 2. So the 2 colors are given here, red and blue. There are 2 partite sets which are shown here. Okay, so thus far we have seen how the chromatic number of graph is affected when it has an odd cycle. In this section we also look at one more graph. The graph shown here is the Peterson graph. You can see that there are some odd cycles here, like the outer cycle, this one, it is an odd cycle having 5 vertices. So let's now color it. So we have after coloring this, we just get this one. So we have just used 3 colors here also, red, green and blue. It is just a matter of simple verification that this coloring is actually a valid coloring. Now we can see that we have got a 3 vertex coloring, and therefore its chromatic number is at most 3, right? And now what is the least number of colors that it needs? That is also at least 3, because it has an odd cycle. So therefore its chromatic number is exactly 3. So thus far we have seen some small examples of computing chromatic number in familiar cases. Now the question arises, when the graph at hand is large, how to color it? So we need some mechanism, we need some technique to color the graph. So in this way, we have a very simple and elegant algorithm that is called greedy coloring algorithm, which colors the vertices in a very simple and straightforward way. And the algorithm is in fact very fast enough. It can color just millions of vertices in just very few minutes. So on any modern computer. So let's look at what this algorithm is and how it works. So the algorithm is this. You just have few steps. Arrange the vertices of G as in some specific order, say V1, V2, V3 up to Vn. And then after that ordering is given, we just assign the color 1 to the first vertex V1. And then after coloring the vertices, say up to V1, V2 and Vi minus 1, we are supposed to color the ith vertex Vi. Now how to color this? To color this vertex, we just look at all its neighbors which have been colored before it. And actually we just look at the colors which have been used on the neighbors which have been colored before it, right? So once we know that information, we just look at the least color which has not been used, and that color can be used to color Vi. So when all the vertices are colored, we can just stop. So this is very simple algorithm. So it just needs some specific order of the vertices. So given that ordering, you start with the first vertex, assign the color 1 to the first vertex, and assign color in a greedy manner. That means you always just look for the least available color which can be used on the current vertex. So that is why this algorithm is known as greedy coloring algorithm. It always looks for color in a greedy manner. It just never uses. We shall shortly see that what is the maximum number of colors it can use on any general graph. So first let's look at some small bounds on the chromatic number which we just skipped. So let's look at the first lower bound. So for every graph G, the chromatic number of G is at least omega G. Omega G is the click number. Click number, you must know that the maximum size of any click in G. That means the maximum size of pairwise adjacent vertices. So the result says that if the graph G has a click of size k, then of course the graph needs at least k colors, because those vertices are adjacent to each other. They are mutually adjacent, and hence they require different colors. So if a graph has click number say k, then its chromatic number must be at least k. So that is as simple. We shall now look at another lower bound, which is in terms of the independence number of graph. So you know that the independence number of a graph is the maximum size of an independent set in the graph. An independent set is just a set which has no edge in between. That means the vertices are mutually non-adjacent. So we have this lower bound. For every graph G, its chromatic number is at least Ng by alpha G. So here Ng is the order of the graph G and alpha G is independence number. So to prove it, we just start assuming let chi G be equals to k, and let S1, S2, up to Sk be the color classes of the vertex set VG. Okay, because the chromatic number is k, so there are k color classes, and let these color classes be S1, S2 up to Sk. Okay, now you know that each color class is an independent set, and therefore it can have at most alpha g vertices. Alpha g is the maximum size of an independent set. So any color class can have at most alpha g vertices, and there are k color classes. So the number of vertices in G can be just, which is the sum of all the cardinalities of the sets S1, S2 and Sk. So this quantity is at most k times alpha g, right? And now we can easily see that k is greater than or equal to Ng over alpha g, which clearly gives us that its chromatic number is Ng by alpha g. So we have just seen two lower bounds on the chromatic number, and we have also seen how the greedy coloring algorithm works. Let's now look at an example to illustrate this algorithm in more detail. So you are given this graph. So to color this, let's first label the vertices in some specific order. So let the vertices be labeled as V1, V2, V3, V4, V5, V6 and V7. Okay, so we start coloring this graph from the first vertex, which is V1. So we will use the usual that ordering, that V1, V2, V3, V4, V5, V6, V7 as the ordering for the algorithm. So V1 gets the color 1. Okay, now to color V2, we just look at number of vertices, the vertices which have been colored before it and they are adjacent to V2 are only one vertex, that is V1. And V1 has been assigned color 1. So therefore the least color which has not been used is still the color 2. So we shall assign the color 2 to V2. Now look at V3. To color V3, again we can see that V1 is the only neighbor which has been colored before it, and the color used on it is 1. So the least color is again 2. So 2 is also assigned to V3. Now we come to V4. So we can see that there are two neighbors of it which have been colored before it, that is V2 and V3, and both of them have been colored by the color 2. So the least color which has not been used is, in this case, 1, right, which has not been used on the neighbors of V4, right? So which is 1, and therefore that color is assigned to V4. So V4 gets 1. Now we just color V5. So again we see that only one of its neighbors have been colored before it, that is V4, which is colored by the color 1. So the least color is available is 2. So 2 is assigned to V5. In the similar way, the color 2 is assigned to V6. And now to color V7, we see that V5 and V6 are the neighbors which have been assigned color 2, and therefore the least color which is not used on V7 is the neighbors of V7 is 1. So V7 gets the color 1. So this way we have seen that the vertex coloring of graph can be found by the greedy coloring algorithm. In fact, there is one point to be noted here, that the greedy coloring algorithm may use different number of colors if we use a different ordering of the vertices. So it is subject to the vertex ordering of the graph. For instance, if you just label the vertices of this graph, you will see for different ordering, say the vertices V4 and V6 are interchanged. So in this case, the number of colors required is 3. But we can ensure that In any case, the number of colors required is at most delta G plus 1. So that is what is guaranteed. There are some other applications of this, like if the degree sequence is given, then we can found the chromatic number in this way. So the bound which is better is this one, the left one. Another application is Brooks theorem, which can also be used. So now we just come to the end of this session. There is one theorem, last theorem, which says that if G is a k color critical graph, its degree is at least its minimum degree at least k minus 1. So we have seen in this session the algorithm, greedy coloring algorithm, and we just looked at some of its applications. We just looked at some examples and how to compute the chromatic number, just estimation of chromatic number using greedy coloring algorithm. So thank you for this session.